Hello. Now let's do the adiabatic process. So first is the explanation in terms of analytical representation as well as the graphical representation. So as we know, there is a ideal gas equation PV is equals to nRT involving three of the variables P, V and T for closed system. If it is an open system, N will also be a variable there. So for adiabatic process, this is not the sufficient. We don't go by three variables. So adiabatic process, there is one more constraint we put onto the ideal gas equation, and that constraint is dq is 0. So adiabatic process is the process in which we don't supply any heat to the system. So there is a container, inside the container there will be gas, and this container, you will make this container such that so that there will be no transfer of heat from the gas to the surrounding or from the surrounding to the gas. So any transfer of heat will not be happening. So that is your adiabatic process. So as you can see, I am putting the constraint in terms of Q, which is not there in ideal gas equation. So what we have to do, we have to convert this dq is equals to 0 equation in terms of equation involving P, V and T. That we will do separately, but I'll write the result there. So when you convert this equation dq is equals to 0 into P, V and T, the equation is going to convert as P V to the power gamma is constant. That's the equation you will get. P times of volume to the power gamma is a constant, and this gamma is defined as adiabatic constant. Adiabatic constant. It's a constant, obviously it depends upon the gas, what kind of gas you are using. And the value of gamma comes out to be Cp upon Cv. When we do the derivation at that time we'll know. And if you put the value of Cp and Cv into the equation, the Cp is F by 2 plus 1 times of R, and the Cv, if you remember, it was F by 2 times of R. So if you rearrange this equation, the gamma will convert into 1 plus 2 by F. And as you can see, this F is a degree of freedom. And the degree of freedom only depends upon the gas, what kind of gas you are using, meaning whether this gas is a monatomic gas or diatomic gas or polyatomic gas. This is your degree of freedom. Degree of. So if the gas is monatomic, we have to put the value of F as 3. So this whole value, the gamma, will convert into 1 plus 2 by 3. That will be 5 by 3. 5 by 3, or we can say it will be 1.67. This is for monatomic gas or atomic gas. The value of gamma for diatomic gas, the degree of freedom will be 5. So it will be 1 plus 2 by 5, that will become 7 by 5. So the value of gamma will be 1.4 for diatomic gas. Diatomic means linear gases. And if you go by the polyatomic gases, the F will become 6 there. So this whole value will become 1 plus 2 by 6 or 1 plus 1 by 3. That will be 4 by 3. So it will be 1.33 for polyatomic gases. When we go for the composition of gases like air, in case of air, there are nitrogen, there is carbon dioxide, there is oxygen. It's a combination of monatomic, diatomic and polyatomic gases. Then we calculate for air, when we calculate gamma for air, that value you can memorize, that comes out to be 1.41 for air. So this value, if you see, it is nearly equals to diatomic, because the main composition is a nitrogen and oxygen. So that is your diatomic, that is equivalent to diatomic. So this is gamma, which is the adiabatic constant. So this is the equation in terms of P and V, PV to the power gamma. We can convert this equation in terms of other variables also, like P and T and V and T, by replacing these values. Okay, so let's do that. So this is my equation of adiabatic process, when actual equation is this, dq is 0. That's your actual equation. We convert this equation, we'll learn how to convert that. We convert this equation by changing the variable from Q to P and V. Okay, so we get this equation. Either you use dq is equals to 0 to define the adiabatic process, or you use PV to the power gamma as a constant to define the adiabatic process. There is no problem in that. Okay, so now what we will do, we will convert PV to the power gamma equation in terms of P and T and V and T. Let's convert first in terms of P and T. So I'll take it as it is, and I'll convert V by the other variable. So if you see the ideal gas equation, from ideal gas equation, if you see, the V is nRT by P. So what I will do, I will replace the value of V in this adiabatic gas equation by this value. So if I do that, it will be P times of nRT upon P to the power gamma is constant. Or we can see P multiplied with T to the power gamma divided by V to the P to the power gamma is equal to, you see, N is a constant. Once it is a closed system, so N is a constant and R is also constant and gamma is also constant. So when you have N R to the power gamma, that is going to be constant. So we'll take it on the right hand side, and the constant divided by constant will give you one more constant, and I'm still writing it constant. So this value, if you see, this becomes P to the power 1 minus gamma T to the power gamma constant. Or let's rearrange this, everything take it on the right hand side. So if we rearrange this value, this whole thing, it is going to be, or let's put it here only, or we can say P and take the root kind of thing. So P T to the power gamma upon 1 minus gamma is constant. This equation will be in terms of P and T, okay. And if you want to convert this equation in terms of V and T, we have to replace the value of P. This is in terms of PV. This is also adiabatic equation, but in terms of P and T as variables. So let's replace this time P. So again, from ideal gas equation, if we replace the value of P, which is nRT upon V. So if we replace the value here, we'll get nRT by V to the power gamma is constant, or we can say it will be T V to the power gamma minus 1 times constant. So this is your equation, adiabatic gas equation, in terms of temperature and volume as the variables there. So you can see, in case of this process we have seen, adiabatic process, in that case the constraint was dq is 0. So what we do, we don't give the value, we don't transfer any heat. It is due to us or it is due to the container what you are dealing with. So the heat given to the system is 0. And when the heat given to the system is 0, we convert that equation in terms of P and V, because we are very accustomed to this format, pressure and volume as a format. And here the gamma is defined as adiabatic constant, and the value of gamma depends upon the degree of freedom from this equation. By changing the degree of freedom, this equation, if you can memorize, it's a good thing. If you keep changing the value of degree of freedom for monatomic, diatomic and polyatomic, you will get different values. And for combination also, you can get the value of gamma. Then this equation of adiabatic process, which was in terms of pressure and volume, we convert this in terms of volume and temperature by replacing this pressure here from ideal gas equation. And we get this equation. This also represents the adiabatic process, but in terms of pressure and temperature. Then we do the same thing for temperature and volume as a variable. Okay. So this is your adiabatic process, and this is analytical form. This, either you use this equation or you use this equation. Any equation you can use, or you can make some different equation also to define the adiabatic process. But this is the actual equation which gives us the condition. Okay. Thank you.